So the next is assumptions of simple bending. So this equation is very important. From this equation only we are going to solve the so many problems in the chapter. Okay, so this is known as M by A is equal to E by R is equal to sigma y. Okay, so each and everything is written here. That is M is equal to moment, okay, and I is equal to moment of inertia, okay, and E is equal to Young's modulus, and R is equal to radius of curvature, and sigma is equal to bending stress, and Y is equal to distance from neutral axis to the mm. Okay, so these are the very important. And let us see the what are the assumptions of simple bending. So these assumptions are very important for solving the problems. So here you can see only bending moment is present and no shear force will be there. In the assumptions, this is the condition, only bending moments will be present but there is no shear force. So you can consider here a beam which is there, okay, from the point C. You can see the movements will be there here anti-clockwise and clockwise. So the bending portion which starts here, which the load falls on the center of the point. So here this will be the neutral axis. So on this point here the bendings only will be there but there is no shear force chance will be there. So that is the first condition, and it is a homogeneous material. So homogeneous material, so it is the in all directions it will be the same. So that's why we will call it as a throughout the length and breadth of the beam it will be the homogeneous material. And next is isotropic material, which is same in all directions, and it is also called as isotropic material because the length and breadth will be the in different and all the same directions it will be there. And the fourth one is center of curvature of beam remains same for all the fibers of beam. So this is the center of the curvature of the beam. You can see here the where the curvature, the bending portion which is acting on the beam, okay, so this states the center of the curvature of the beam. So it will be in the same condition for the beam, okay. And fifth one is transverse section of the beam are plane before and after loading. So this is the main point. So what is the transverse section here? When the beam cuts the beam at the center of the point, okay, so half portion which is there, that is nothing but this one. So in half portion you can see a neutral axis will be constant. So the cutting section which is known as, that is the transverse section. So here in which side if you see it looks in the square or in the rectangle, whatever the beam in the shape, okay. So the transverse section of the beam are plane before and after also loading. And the sixth one is elastic limit, that is known as Young's modulus of the material is same in tension and compression. So here there will be no chance of changing in the material, okay. So coming to the next point is neutral axis. This is very important. What is neutral axis? So it is a line on the neutral plane on the beam cross section. It is a line on the neutral plane on the beam, that is known as the cross section at the center of the point, which is known as the, for every structure, that is a neutral axis. And here all fibers situated above neutral axis are under compression and those below it are under our tension. So here see, let us see the consider an example, that is known as a beam, okay, a rectangular beam which we have considered here. So this is the center of the point is known as neutral axis, okay, and this is a considered a elemental strip, so that is known as here. So for sagging we can see positive moment, for hogging negative moment. So let ABCD is the cross section of a rectangular beam that is subjected to positive bending, okay. So every time we have to take the positive bending moment. So in this is a rectangular beam, so this is known as the ABCD, okay. So this is the cross section of the beam, and here this is a strip. So taking here this is known as a sigma A. So A is known as area of the strip. So whatever this shaded portion is there, that is the called as area of the strip. So from the top of the at the center of the neutral axis, that is described as Y, and this portion is YC. YC is nothing but compression and YT is nothing but tension, okay. So in this condition the bending stress will be in this direction. You can see here the forces which are acting here, this will be in the compression state and this will be in the tension state, okay. So that means from the beam the forces are acting in the one of the in the top or in the horizontal condition. So we can see here that is known as Consider a small strip of elementary area sigma a situated at a distance y from the neutral axis Na. So that is known as this one. So this is known as the sigma a. It is from the neutral axis y. Okay, and now the stress on elementary area is equal to y into E by r. So that is E is equal to Young's modulus and r is equal to radius of curvature in mm. Okay, so Young's modulus will be in the Newton per mm square. Okay, so that is known as y into E by r. So that is stress in the elementary area is y into E by r. So where is y here? So this is the y. So on y we can see that is the stress elemental area is y into E by r is described as nothing but sigma a. So, and force on this strip is equal to stress into area of the strip. On the strip, whether it is stress into area of the strip. So, stress is here we have got that is nothing but y into E by r into sigma a. So, the total force acting on entire cross section of the beam will be the sum of all such forces between the limits, that is yc and yt. Yc and yt is nothing but between compression and tension, the total force will be acting on the entire cross section of the beam. So it is described as derivation, that is nothing but is equal to yc compression integration of yt, okay, into y into E by r into sigma a. So this is described as E by r into integration of yc yt. So y into E by r is nothing but written as here you can see sigma a into y. So the integration it has takes is equal to E by r integration of yc by yt, that is here it is written as sigma a into y is equal to 0. So but here the condition, the E is not equal to 0 and r is not equal to 0. That means the shear force or resultant whatever it may be, you can see. So E by r is equal to integration of yc by yt sigma into a. Sigma a into y is equal to, that is nothing but sigma a is the area of the strip, that is written as a, into y is nothing but y bar. So here a is equal to total area of cross section and y bar is equal to distance of center of gravity of entire cross section from neutral axis. So but a is equal to area of cross section is not 0, but y bar must be equal to 0, that is written as y bar is equal to 0. So that means here, so what we states that is from the above condition is, from the above it is clear that the first moment of area of beam section about its central axis is 0, but in the second the neutral axis of the beam passes through the center of the section. Okay, so from these two conditions our theory of simple bending will be solved. So that is known as the neutral axis condition. Okay, so hence neutral axis passes through the central axis of the beam. So this is the condition here. Okay, so this is regarding the our theory of simple bending topic. Thank you.